In this video, I will actually go over scientific notation and significant figures. So a little bit of a review. So those will be the two items that I'll review briefly, and I will get into a new topic, and that's going to be the topic of introducing fractions. So the agenda for the video is the following. First, I will review scientific notation, and secondly, significant figures. And once I do that, I will then get into the introduction to fractions, where we will do several topics. One of the topics that we will have is prime numbers, which is going to lead us into composite numbers, so understanding the difference between these two. Then I will take the concept of prime numbers and composite numbers and show how any number can be prime factorized. Once that is done, I will get into the divisibility tests, and I will only cover divisibility by the number 2, number 3, number 5, and number 10, meaning if you take any whole number, when is that whole number divisible by 2 or by 3, by 5, or by 10? So how we can quickly see that divisibility. So after that, we'll talk about naming of fractions, so utilizing cardinal and ordinal naming to name fractions properly. And finally, the last topic will be proper, improper, and mixed numbers, and that will end the video. So let's get started. So the first item that we have, so this is mainly a review of scientific notation first. Scientific notation. And I will do this through several examples. First example is in terms of equivalence. So if we want to have two numbers to be equivalent, recall that I have taken this up as calling smaller bigger, keeping that in mind. So here is the example that I'll give. It is negative 245 and 328 thousandths times 10 to the 427, and that equals to negative 24532.8 times 10 to an unknown exponent. So we have equivalence because of the equal, so left-hand side is supposed to equal to the right-hand side. I know actually everything on the left-hand side of the equation. So I know my significand and I know my exponent. On the right-hand side, I know my significand, but I do not know my exponent. So if you recall, in these questions, we always try to deduce the answer from going from the side that we know, so in this case the left-hand side, and we're going to put an arrow towards the right-hand side to our unknown, which is our question mark there. So because I know both significands, then all I can see is, okay, so what has happened in magnitude to this number? So magnitude ignores the sign, so it is going to stay negative. But if I ignore that sign, I notice that my decimal has shifted over by 2 spots. So it has shifted over by 2 spots. And in magnitude, that means it got bigger by 2 powers of 10. And once you notice this, then the exponent, when you're shifting over to the right-hand side, in order to balance, so since this got bigger, therefore the exponent is going to have to get smaller by exactly the same amount, okay, but getting smaller by powers of 10, okay, is subtracting the exponent by 2, and it's going to give us an answer of 425. So that question mark is 425. And that was a concept of bigger, smaller, trying to go from one side to another. Okay, so that's one example in terms of a review. Let's take a look at another example. Okay, so this one slightly different, okay, and on a different topic. Okay, if you find that the topic that I covered you need more clarity on, you will have to take a look on your own to try to do more examples. So the second example that I have, and what I want to review, is related to now multiplication and division, okay, between scientific notation numbers. So for instance, let's take a little bit harder example. So 6 times 10 to the power of 725 multiplied by, let's say, 9 times 10 to the, let's say, negative 100 divided by, and these numbers are just random for the moment, divided by, let's say, negative 3 times 10 to the negative, say, 152. And we want to find our answer. So this is a nice example because it forces us to review both multiplication and division of scientific notation. Again, so we can't really use calculators, and the way that I've structured it, it wouldn't really help you much. Okay, so please remember that once you're starting on these questions, once we have our base of 10 and it has an exponent, that helps us a lot, because when we notice this, all we have to do is now take our, in this case, mantissas, and work with them first. So I will take this 6 and first, okay, so I'll multiply it by 9. Now 6 by 9, I'm going to do it here, I'll scroll down a little bit. So 6 times 9 is 54, so that is that. And now I will divide, okay, so by this negative, okay, so 3 in this case. So I have something like this. Now, if you can't do it off the top of your head, it's fine. You should notice that the answer is negative, okay, and, okay, if you don't want to do it in your head, you can do just the long division. So 3 goes into the 5 once, so 1 times 3. Now I'll subtract to see what remainder is left over, which is 2. Bring down my 4. So 3 into 24, okay, so goes in 8 times, and 8 times 3 is 24, so it nicely comes out. So my answer is negative 18. Now you could have done this in your head if you wanted to. So that takes care of the mantissa. Okay, so I multiplied these two first, and then I divided by -3. Done. Now, because I have these exponents and the base is 10 everywhere, okay, so here, these two exponents, because I have multiplication, and there's, so don't forget there's a multiplication between these scientific notations in front of that bracket. So, here on the right-hand side, I know that because I'm multiplying, I will have to add these two. Now, you have to be careful because I am adding a negative here and a positive in front and a negative, okay, number. So that turns into a subtraction. So 725 actually minus 100. Now this one is a little bit easier to do. You should notice that it is 625. So although we are adding right here, because of this subtraction that we have, okay, which is right there, it turned into a subtraction. Great. So that takes care of these two. Now what I have is I have this -152. But here we're dividing. We have this fractional division. Okay, so within here, so we have this fractional division right here. And that fractional division is going to tell us that we're going to have to subtract. So we have 625 minus because of the division, but we're subtracting a negative number. So now, again, if I look at the two signs side by side, so that actually turns into addition. And that addition, okay, so we can do, so let's line these up. And we're going to add them together. So 5 plus 2, so that's 7. Oh, 2 plus 5, so again is 7. Oh, look at that, all 7s. Okay, so that is my exponent. So the answer, if I bring these things together, is I have -18, that's from right here, times, so the base stays the same, and the exponent is 777. Finally, you have to be very careful because you need your answer to be in scientific notation. This is not, because the mantissa in magnitude, notice, is 18. So I am going to change this, so the negative stays the same, but I need my mantissa between 1 and 10. So I'm going to shift, okay, so this decimal that's in the back, and notice what I've done is I've made 18 smaller, okay, so that I get 1.8, meaning I had to divide by 10. So what happens to the exponent? It has to get bigger. And it will get bigger by 1, which is the same, okay, as the shifting of the decimal. So this is going to be 778. And that is your final answer. So if I zoom this out a little bit, okay, so this is what we would have for this question. It's a great question because it challenges you to remember what to do in multiplication of scientific notation numbers and what to do in division, all in one step. Okay? So that is our second example as part of our review. So let us continue. So now I will take a look at a third example. And this example is to illustrate and try to review the concept of addition and subtraction of scientific notation numbers. So let's imagine we have the following question. I'm going to write it out for us. and we are supposed to solve this. So let's take a step back. In addition and subtraction, in this case, now it could have been all addition, it could have been all subtraction, but if you're going to add and subtract scientific notation numbers, you should recall that in this case, you're not going to be doing adding or subtracting any of your exponents. What you have to make sure is that your exponent is the same. Now, it is not the same in this case. They're all different. So what we must do is you can, in one of the ways, is to simply take your largest exponent. Now, our largest exponent is the smallest negative. So be careful with that. Again, your largest exponent, okay, is the smallest negative. If these were all positive, meaning 582, 581, 580, then our largest exponent would have been 582. But because they're negative, you have to pick the smallest negative. Now, once we do that, we're going to just leave that number as is, meaning we're not going to change it at all. The exponent and the mantissa will stay the same. But for all the other ones, now we're going to have to change them so that they are identical, because we want to have the same exponents. And if we do that, so if the first one, notice we have increased it by 1, so we have to add 1 to negative 581 to get negative 580. And that is going to turn, okay, the 3, since we've made this bigger, the exponent we made bigger, this is going to have to get smaller by 1, okay, and that will shift the decimal 1 over to get 0.3. And now the last one, so this, as we switch it over, again, we have to make it negative 580 so that they are all the same as they are now. But if we do that, we have to make the number equivalent. So we have made this bigger by 2, and therefore this is going to get smaller in magnitude. So it still stays negative, but our decimal is going to switch over by 2. And that's what we have. Now, because the exponents are the same, this question boils down to simply working with our significand and our mantissa at the end. So let me pull these out from here. So we have negative 0.09 plus 0.3 minus 5. Okay, and now this tests our ability to do subtraction and addition, okay, of decimals. So first off, these two. So, okay, I have a negative 0.09 plus 0.3. So I'll take the bigger, okay, so 0.3, okay, and I will subtract the smaller from it. Okay. Now the answer is going to be positive here. Okay, so here there's a 0. So 0 minus 9 I can't do. So that's going to switch. This is a 10. Okay, so that's 1. And then 2. And nothing left there. So those are my first. Now I have to subtract negative 5. Okay, so it's like having 21 cents and then you go out and you spend $5. So you're going to be in debt. So you're definitely going to, your answer is going to be negative. So the way, if you don't see it, okay, so the answer is actually 4.79. If you don't see that, remember what you have to do. you have to take the bigger in magnitude, so that's 5, and subtract the smaller, okay, in magnitude. And now notice I have nothing to subtract, so we have to kind of insert, okay, so fake zeros there so that we can actually work with this. And I'll change color so it's very visible for you. So 0 minus 1 I can't do, okay, so I'm gonna, now I cannot take away from 0, okay, so what I'm gonna do is I have to take 1, so I have to turn this into a 10, correct? But if I took 1 away, that 5 0 is going to turn into 4 9, okay, because you took 1 away, okay, and that 1 ended up right here. So now 10 minus 1 is 9, 9 minus 2 is 7, and then here's our 4. And notice that's exactly what I put there. All right, so that finishes. Now luckily it is a mantissa, it is between 1 and 10, and then we can finish this off and simply say 10 to the negative 580, and that would complete this addition and subtraction. So that is a review, okay, of the concepts that we had, okay, in scientific notation. So bigger, smaller, making sure we know how to shift the decimals. We should know how to multiply and divide, scientific notation, and we should know how to add and subtract. So these are 3 examples. Please go over them, make sure that you understand what was done. The other concept that I wanted to review with you is significant figures, or sometimes they're called digits, and I very often like to just simply say sig figs. That's all. So these significant figures, in order to count, because this is what significant figures are about, we want to count how many digits in a measurement are actually significant and part of the measurements. Okay, so how precise our measurements were. So let's do this by examples. Okay, there's basically 2 rules. First rule is that all non-zero digits are significant, so they always count. And then the second rule has to deal with zeros. So zeros on the left never count. Zeros in the middle always count. And zeros on the right only count if there is a decimal in the number. So, as a shorthand, so number 1, non-zeros, so non-zero digits, always count. So that's 1. Rule number 2 has 3 cases. There are zeros on the left. Now, it is zeros on the left of the non-zero digits. These ones never count. Then there are zeros which can be in the middle. They're sandwiched in between significant digits. These always count. And finally, when you have zeros which appear on the right of the significant digits, they only count if there is a decimal in the number. That is important. Let's try to do these by examples. Okay, so first example, we have 2600. So if I go through this, I know, well, here are my non-zero digits. Okay, so that's right here from rule number 1. Well, they always count. Now I have 2 zeros. Now these zeros are on the right here. But those zeros only count if there is a decimal in the number. There is no decimal in the number. Therefore, this number has only 2 sig figs. And as part of our review, do not forget that your last significant digit on the right is called the estimated digit. So that's example 1. Here is another example. So this one, almost the same, but I'm going to stick in a decimal. So again, the 3 and the 2 count. And now for our zeros, notice it is zeros to the right of the non-zero digits, not of the decimal, of the non-zero digits. And now, do they count? Well, if we go to our rule, it says that if they're on the right and there is a decimal, then they count. So these all count, and we have 4 sig figs. And our estimated digit is our last one. So that would be the last 0. That's another example. Here is a third example. So for our third example, what if we have something like this? So let's count them up. So these ones are always easy. Okay, so they count because they're non-zeros. Now we have zeros on the left of the non-zero digits. Okay, so they're to the left. Again, if they're now, if I scroll back up, so if they're on the left, they never count. Never. Doesn't matter if there's a decimal or not. So in this case, only 2 sig figs. And again, our estimated digit is our last one. That actually counts. Okay? Last example. This one's a little trickier. I'll try to throw in everything I can into this one. So we have non-zeros always count. Okay? Now, there are zeros on the left. Zeros on the left never count. There's a 0 in the middle. If you go back, notice in the middle always counts. So this one counts. Now there's a 0 on the right, and this one also counts because there is a decimal in the number. So in total, 5 sig figs. Perfect. So this illustrates the sig figs review, and hopefully you found this useful in terms of counting them up. So that finishes our review. So let me scroll up, okay, to our agenda. Now we're going to concentrate on this topic, which is the introduction to fractions. So, for this topic, this is Intro to Fractions. Well, fractions, as we recall, are simply rational numbers because they can be placed in fractional form p over q. Now, before we get into fractions and start talking about, having a numerator on top and then having a denominator at the bottom, it is very wise of us to begin and first proceed with trying to understand a topic which is called prime numbers. Now, you may recall whole numbers, okay? So for whole numbers, they were defined as and so on. Now, we could have started with natural numbers, which wouldn't have the zero. But in any case, for prime numbers, okay, prime numbers, they're also a set. But they are only a set of numbers that only can be divided, only divisible, so can only be divided by 1 and itself without having any remainder. Now, what are these prime numbers? So by definition, so we're going to omit 0 and omit 1. Okay, we're going to start with the number 2. So number 2 is indeed prime, because if you take any other whole number, aside from the 0 and the 1, it can only be divided by 2 itself. And now 3 is your other prime number. Again, okay, notice 2 does not go into 3, at least not evenly. Okay, now 4 is not a prime because I can divide 4 by 2. Okay, and it does go in evenly, and therefore it would not abide to our definition here that it can only be divided by 1 in itself. So 4 is not prime. Okay, now those numbers that are not prime are called composite numbers. So I'm going to do them side by side. So we started, so first was 4. Okay, now what about 5? Well, 5 is prime, can only be divisible by 5 in itself. Nothing else will go into it evenly. So it can't be composite. 6. 6 is divisible by 2 or by 3. Okay, so therefore it is composite. 7. 7, you can check, is a prime. And now you can play this game. So now 8 will be composite. 9 will be composite. It's divided by 3. 10 is composite. Okay, so the next prime one is 11. And then you can go through these and you'll see 13. Okay, 17, 19, and it goes on actually forever. I don't know all the primes because, again, they go on forever. But if you know the top 20, okay, you'll do very well. Okay, so you're going to have to try to memorize these top 20 and remember these primes. Now, on the opposite end, the composite numbers, so 4, 6, okay, so the next one was 8, then it was 9, 10, Okay, so 11 was prime, so 12. And then again, this goes on forever. So those are prime and composite numbers. Now, the nice thing is that all our composite numbers that we have can actually be written as a multiplication of primes. So what I mean by this is the following. If I take 4, I know that 4 is equal to 2 times 2. Now, 2 is prime. If I take 6, I know that 6 is 2 times 3. Again, notice 2 and 3 are prime. If I take 8, 8 is 2 times 4, but 4 from above we know is also 2 times 2. So notice 8 is also made up of 2, which is just prime. And you can go on and do any sort of number that you please. I mean, it can be a huge number, okay, if you wanted to. Okay, so for instance, we can take 56. Okay, so now 56, if you take it, okay, so 2 goes into 56 times. Now, how many times does it go in? Okay, you can check. You don't have to remember off the top of your head. Turns out that it's 28. Now, the 28, okay, so this right here, we can also break down, okay, into 2 times 14. Now, the 14 can be broken down into 2 times 2, 2 times 7. Now, I can't break 7 down any further. So what you're finding is that you can take any composite numbers and divide it into, you get what is called a prime factorization. So you're factoring, so these are factors. So for example, this has 4 factors, this has 3 factors, this has 2 factors, and this has 2 factors. And their factors are all prime. So we call this prime factorization. So any number can either be a prime or it can be a composite number that we can break down and write it in terms of prime factors. So now this is going to be useful for us because as you get into fractions, you'll notice that doing reducing of fractions, doing multiplication or additions, okay, when you have various big expressions, knowing primes is extremely useful. Okay, and you'll see that down the line. So learning primes and learning composites, okay, is a useful tool to have to make your life easier with fractions down the line. So now these prime factorizations, you've noticed I kind of did them off the top of my head. Now, is there any help? Okay, because sometimes you may get a very big number and then you might have to prime factorize and you don't know which primes go in. Of course, you can just simply divide and then check, but there is another tool that is used, and it is the tool of divisibility. So the divisibility test, it is useful to know when a number is divisible by 2, by 3, by 5, and by 10. For instance, if I give you something crazy, okay, which would be, a big number, not that I would make you prime factorize this, but I just want to show you that you can very quickly check when these when this number is divisible by any of these. Okay, so first of all, divisibility by 2. Okay, so this right here. When can we divide by the number 2? When can we very easily see? Well, it turns out that a number is divisible by 2 only if it is even, meaning it ends, so the last digit, this digit, it ends in a 0, a 2, a 4, a 6, or an 8. So this huge number that we have, instead of dividing by 2 and checking if it goes evenly, all you have to check is, okay, is it even? It's not even because it ends in a 5, so you would know right away that you would not be able to divide this by 2, and therefore 2 would not be a factor of this number. So that is 2 right here. I'm going to skip 3 for a second, okay, and I'm going to take a look at 5. So when is a number divisible by 5? So this one is even simpler, okay? So that 5, okay, it's divisible by it only if it ends in a 0 or a 5. So for instance, if we go back to our number, it ends in a 5, so you would know that 5 is a factor of that number, okay? It actually divides it equally. Now 10, and I know you might say, well, 10 is not prime. However, 10 is nothing else but 2 times 5. So, when is a number divisible by 10? Well, that is even simpler, okay, if it ends in a 0. That's it. So here is an interesting case. So you might not have to do something crazy and do prime factorization of this. But you might run and be asked an example like this. Try to prime factorize 450. So here, if you know your divisibility test, you can notice that, hey, wait a minute, it ends in a 0. So that means it's divisible, okay, by 10. Well, okay, so this, okay, is divisible by 10. Okay, so I can very quickly break this up into 45 times 10. And now 45 is much simpler to prime factorize. So you may know this is just 5 times 9. And 9 is the same thing as 3 times 3. So that is the prime factorization of 45. And now 10, well, 10 is just 2 times 5. So in total, okay, your prime factorization of 450, you have 5 times 3 times 3, which comes from 45, and then times 2 times 5, which comes from the 10. And there you have it. You prime factorized 450. Okay, I will note that when you are doing this prime factorization, very often we try to write these numbers, okay, from smallest to largest, but we don't have to, because the factors multiplication, okay, the order is irrelevant. Okay, so let's recap. We have divisibility test, okay, of 2, 3, 5, and 10. So all I've talked about is divisible by 2 only, okay, if it is even. Divisible by 5 only if it ends in a 0 or a 5. And divisible by 10 only if it ends in a 0. So far, so good. These ones are simpler. The one that's a little bit harder to know, okay, is this divisibility by 3. So let me show you, okay, as an example. Okay, I'll write out the rule. Okay, so it's divisible by 3 if the sum, so the addition of all digits is divisible by 3. So what does this mean? So I'm going to rewrite the number that we started with. Okay, so 2, 7, 8, 1, 4, 6, 5. So taking the sum of the digits literally means, okay, so 2 plus 7 plus 8 plus 1 plus 4 plus 6 plus 5. So I am literally just simply adding up all the digits. So now you can add this up. If you don't believe me, okay, you can try it on your own, and it will add up to 33. Now notice, what this statement says is that instead of checking if 3 goes into basically this, humongous number of 2,781,465, you can just add the digits, okay, and now you have 33. Now 33 is much simpler. Does 3 go into 33? Yes, it does. So which means that 3 is divisible into, okay, this giant number over 2 million. That is the divisibility test. Now, another example from the previous one that we did, okay, so if they're even a little bit smaller, so notice we were dealing with 450. Now, we already know that 450 is divisible by 3. So if you look up here, okay, we already have these factors. But what you could have done, you could have said, okay, let me add the digits. 4 plus 5 plus 0, that's 9. And then ask the question, well, is 9 divisible by 3? Yes. Therefore, so is 450. So that is the divisibility test for 3. All right. So we have prime numbers, we have composite numbers, we have talked about prime factorization, and we have talked about the divisibility by the numbers 2, 3, 5, and 10. Now, let's take a look, okay, and talk about naming, okay, of fractions. So, naming of fractions, okay, in a proper way. So I'll give you first, okay, so there's some common fractions. For instance, this one, probably everyone knows, we typically say is simply just 1/2. Or, a half. This one, okay, we say it is a quarter, or just simply 1/4. There's some brackets here. I'll put a quarter. Those are the most kind of common ones. So, 3/2, 5/2, or 3/4, and 5/4, or 10/4. Okay, so basically it's fractions over 2 or over 4. So that is something that you should be accustomed to, okay, as time goes on. But now for most other fractions, there has to be some way, of deducing how to name the fraction properly. For instance, if if I give you 11 over 5, now some people might say 11 over 5, but that's not the proper way of saying it. So what we do is we take the numerator and we say the numerator as a cardinal, meaning 11. Then we take the denominator and we say the denominator as an ordinal. So 11 fifths. Okay? So notice that we have this is as an ordinal. It's with an S because it's plural, because we have 11 of them. And the numerator we say as a cardinal number. So that would be 11 fifths. Here is another one. So let's say I have something like this. So again, I will take first the numerator and just say it, okay, as a cardinal, so 20, 1, okay, with the hyphen. And then I will take the denominator and say it as an ordinal, so 30 sixth. And then I'll add an S because I have 21 of them, so 21 36ths. Okay, so that would be the proper way of saying that. Okay, another common thing is sometimes you'll have them mixed. So for instance, something like that. Okay, so what we do is our whole component, okay, again, so you say as a cardinal. So this would be 3. And just like in decimals, then we will say and, because now we have a fractional component, 4 elevenths. Okay, so that would be 4 elevenths. Notice 4 from the top as a cardinal. 11th is an ordinal, and with an S because there's 4 of them. Okay? And now, lastly, if you get, let's say, 1 over 10, that would be 1 for the 1, and now you would say 1/10. Notice there is no S now because there's only 1. Okay, so it's not plural. So that is naming of fractions, which you can practice. If you know cardinal and ordinal, okay, you should be able to understand these examples. Okay? So in order to wrap this up, okay, so this video, I'll finish off and talk to you about the last topic of, so proper fractions, improper fractions, and mixed numbers. So first off, proper fractions. So what are proper fractions? Well, by definition, if we have a fraction, which is a over b, we say that it is proper, okay, so if and only if, okay, our numerator is smaller than our denominator. Okay, so examples. 1 over 2 is proper. So 3 over 7 is proper. 11 over 212 is proper. Okay, and so on. These are proper because the numerator is smaller than the denominator. Okay, that's 1. 2, improper. improper fractions. Now, if we have A over B, we say this is improper if A is bigger or equal to B. So A, meaning the numerator, is equal or bigger than B. So some examples: 3 over 2 is improper. 7 over 4 is improper. 11 over 11 is improper. So remember, they can be equal, but they're still improper. Those are improper fractions. Finally, when you mix numbers, so mix numbers between a whole component plus a proper fraction. Meaning, if someone gives you a fraction that looks like this component would be a whole number, and this fraction has to be proper. So if it's improper, then it's not considered a mixed number. Okay, it would be none of them or neither. So for instance, 3 4/11ths, that is a mixed number. But 3 and 8/7 is not a mixed number. So remember that difference. It has to be proper. Has to be proper. Okay, so here are some examples, and you can guess them as we go. I'm going to write them down, and you can guess if it's proper, improper, mixed, or neither of them. And then I'll tell you what the answers are after I finish writing. So test yourself. All right. So the first one, what did you say? That one was, it is proper because the numerator is smaller. Second one, so yes, it's negative. We're looking just at the magnitudes. This one is improper. Okay. Third one, this one is mixed. Fourth one, this one is improper. And the last one is none of them. I'll put N for neither of them. Okay, and that's because we have 2 over 2. And we need that fraction to be proper if it's a mixed number. All right. So that is now an introduction to all of these components. Okay, so I'll stop it here so that you can review this, and I want you to test yourself to see if you can change, for instance, an improper fraction back into a mixed number. I want you to try that. Okay, so an example of this, so just so that you see it, for instance, 27 over 2, that is improper. If you want to change it to a mixed number, so we're going to divide 2 into 27. Okay, so how many times does that go in? And you will notice it goes in 13 times. And now our remainder, so let me just do it right here. Okay, so 2 into 2 once. So subtract, bring down the 7. 2 into 7 goes 3 times. 3 times 2 is 6. And notice we get a remainder of 1. This remainder you put on top, and now you've created a mixed number. So I want you to try, okay, so some examples like that. And now you should also be able to do the reverse, meaning take a mixed number and change it into improper. So you get 7, let's say 3/5. How do we change it back? Well, we have to know we have 7 whole components. So we take those 7 whole components, okay, and all of them are made up of 5 pieces. So 7 times 5. And then we still have 3, so plus 3. And that gives us, so 7 times 5 is 35, plus 3 is 38. And that is 38 total pieces out of 5. So I want you to practice several questions like this. Okay, you can test yourself on your own so that you're ready. Okay, we come back to this. All right, so thank you for watching, everybody. I hope that you find this useful. Okay, please hit a like if you find it useful, or leave comments. Okay, so they're greatly appreciated, because then I'll know if you are able to cover this and understand it. Okay, have a wonderful day.